We will learn how to figure out kinetic and thermodynamic products for dienes that are not symmetrical, which is a more complicated case. So here I drew a diene. It is conjugated double, single, double, and you can see that the two double bonds are not the same. This diene is not symmetrical. So how would we know how to figure out the kinetic and thermodynamic products? The first question is, what double bond should I choose to attack HCl? Should I choose this one or this one? And the answer is you do not know which one just by looking at the molecule. You must go through both double bonds to see which one will give you the most substituted carbocation, and that is the pathway you will choose. So let me go ahead and guide you through that. Let's call this double bond A, and this one will be B. Let's say that I'm going to go through the A pathway. Let's say this is the double bond that will attack HCl. So I'm going to go ahead and I will attack hydrogen, and this bond will break, and this double bond stayed here. Now one of these carbons will get a hydrogen, another gets a positive charge, becoming carbocation. You always want to put your carbocation closest to the second double bond because that carbocation will be resonance stabilized. So you always, whenever you do this kind of problem, you always want to put your carbocation next to the other double bond so that it can have resonance and be more stable. So I'm going to put my positive charge on this carbon, and this will have my hydrogen. Next, what you want to do is you want to show the resonance. The resonance is from double bond to the carbon like this. And so my new double bond is here, and now my carbocation is here. That's the first pathway. Let me change color for the second pathway. Now let's try pathway. Let's try to use double bond B to attack hydrochloric acid like this. And I will use a different color so we don't get confused. So bond A stays the same, and in this case it's this double bond that must get protonated. And where do I put my carbocation? Again, I always put my carbocation closer to the other double bond, which is called the allylic position. Even though this position would be more substituted, this position is actually more stable because it is resonance stabilized. So I'm putting my positive charge here, and that means my hydrogen must have one there. Now I'm going to show my resonance, and my resonance goes from the double bond to create a new double bond. And so where's my new carbocation? This carbon lost the bond, so it becomes a carbocation. So these are the two pathways. This is pathway A, where we use this double bond, and in pathway B we use this double bond. Let's now compare the two pathways. Let's go ahead, and what we're going to do is we will go ahead and figure out what kind of carbocations we have. Are they primary, secondary, or tertiary? This carbocation, this carbon is connected to 2 carbons, so it's secondary. This carbon is connected to 3 carbons, so this is a tertiary carbocation. This one is secondary, connected to 2, and this one is secondary as well. So now that we have shown both pathways, breaking both bonds, we can see which one will work best based on the carbocation stability. We can see that when this was A and this was going through B, we can see that when I used double bond A, I created secondary carbocation that had resonance with the tertiary carbocation, creating tertiary carbocation product. For pathway B, I had secondary and secondary, so that is not the pathway. Again, we tried both double bonds. Double bond A gave me a secondary and a tertiary carbocation. Double bond B gave me 2 secondary carbocation, which means A wins because it has a more stable carbocation, so B is not the pathway. So we just learned from doing this that I have to use this double bond first to attack HCl. That's the double bond that attacks HCl because it will give me the most substituted carbocation. Now I'm going to go ahead and ask myself which product will be kinetic and which will be thermodynamic. So kinetic product is the product that happens fast, and it happens before the resonance. So if I use this carbocation and I have Cl minus, it will go ahead and attach here, and I will put chlorine here and hydrogen here. That's one of the products possible, and I will also tell you how to determine which is kinetic, which is thermodynamic. Let's just show both products that are possible, and then we will go through our steps actually. Okay, so here again Cl minus can attack this carbocation and attach here. Okay, these are the two products that are possible. Now, kinetic product happens the fastest, and so it is the product that happens before the resonance. It doesn't have time to do the resonance. Chlorine is right next to this carbocation and it attaches. So this product will be kinetic, and we also call it 1,2 product. Because if we number here, this is 1, 2, 3, 4. We can see that hydrogen 1 on number 1, and this is number 2, 1, 2, kinetic. Thermodynamic sometimes is the other product, but sometimes it's not. Sometimes it is 1, 4, and sometimes it is 1, 2. Thermodynamic product is the product that has the most substituted double bond. So now let's compare our two products. The product on the left, the double bond is connected to this carbon, and this carbon. So it's tri-substituted. The double bond on the right is di-substituted. So this actually is the more substituted double bond as well. So not only in this case is this our kinetic product, it is also our thermodynamic product. Okay, so just to reiterate, because this is a more complicated problem, if you have a problem where your molecule has two different double bonds, the first thing you do is you use each double bond to see what kind of carbocation intermediates there will be. So if we use A to give us these two this carbocation intermediate that had the resonance to produce this. And then we did the same for B. Next, we compared our carbocations for the two pathways. Pathway A gave me a secondary and a tertiary carbocation. Tertiary happened after we did the resonance. Pathway B gave me both secondary carbocations. It has to attack first. Now, after I got these two intermediates, I have to figure out which one is kinetic and thermodynamic. I first showed the two products that were possible by attaching chlorine. And then I look at the products. The one that happens right away before the resonance will be my kinetic product because it happens really quickly, and chlorine is right next to the carbocation before it gets a chance to do resonance. Now the second thing is that this product in this case also turns out to be thermodynamic, because thermodynamic product is the one that has the most substituted double bond, and in between these two options, this double bond is tri-substituted and this double bond is di-substituted. So therefore this product is both the kinetic and the thermodynamic product. This is Maya from Transformation Tutoring, and I hope you're enjoying my videos, and I look forward to seeing you in more organic chemistry and general chemistry videos.